All right, guys, we are going to be starting notes today, and a couple of things. First of all, this first unit is going to talk a lot about some of our trig basic stuff, a lot of right triangles that will continue throughout the semester. Um, a lot of y'all stopped in Algebra 2 back in March with a lot of this trig content, so us pre-cal teachers know that and know that. A lot of this stuff will be new for you. So we have the time built in to make sure that you are getting all this new content down. A couple of things, housekeeping stuff with these notes. You are more than welcome to print off the blank note sheet that I provided on the Schoology site if you have access to a printer, and then you can just follow along with this video. If you are taking notes by hand, um, that is also absolutely fine. Make sure that you are labeling the top of your paper with the name, with your name, sorry, and with the label of your notes. So as you can see up at the top there, we are going to be talking about the Pythagorean theorem today, which should strike a chord with y'all. Y'all are familiar with that, and with special right triangles. So you can see that the notes are kind of divided in two. We have Pythagorean theorem and special right triangles. So if you are taking notes by hand, or if you are printing them off, not if, when you're taking your notes, I expect your notes to be thorough. I expect them to look like mine. I expect you to be able to use them when you're studying for your assessments in the near future. So let's go ahead and dig in first on this Pythagorean theorem stuff. Probably remember the Pythagorean theorem back in the good old days of geometry. The Pythagorean theorem allows us to find missing sides of right triangles, meaning that they have a 90-degree angle right here, represented by that small box in the corner. And a right triangle has two pieces. The two sides that are connected to the right angle we call legs. And then the side that is across from that right angle is always the longest side, and it is called the, hypotenuse. The Pythagorean theorem states that the leg squared plus the leg squared is equal to the hypotenuse squared. You have also probably heard it as the legs being a and b and the hypotenuse being c, so you can plug in the variables a squared plus b squared equals c squared. Again, this only works, with right angles, right triangles. So if you don't have a right triangle, then you cannot use the Pythagorean theorem. But it is a very helpful tool that we can use to find missing sides of right triangles. So let's take a second. By the way, when you're watching this video, remember that you can always freeze the video, pause, and write down anything that you might need to or rewatch as needed. So let's go ahead and label the missing pieces here. So we have across from the right angle, that's our hypotenuse. We're going to label that C. A and B are both the legs. They can be interchanged. It doesn't matter. And let's plug those pieces into the Pythagorean theorem. So we have x squared plus 11 squared equals 13 squared. Keep that calculator close by so that you can find those values on your own. X squared plus 121 is equal to 169. We want to isolate this x squared, so we subtract the 121. We got ourselves x squared equals 48. And then if we want to isolate x squared completely, remember the inverse of squaring a number is taking the square root. So we're going to take the square root of both sides. Square root of x squared is x equals the square root of 48. Now, a couple of things. You could plug that square root of 48 into your calculator and get a decimal. When we are doing these problems, we're going to want to simplify those square roots completely and not write as a decimal. When you're simplifying square roots, you're trying to think of what perfect squares fit into 48. Perfect squares can come out from underneath the square root. Remember that, your perfect squares, I don't want the highlighter. Your perfect squares that can come out from underneath radicals Well, 1, but that doesn't usually help us. 2 times 2 is 4. 4 is a perfect square. 3 times 3, 9. 4 times 4, 16. 5 times 5, 25. 36, 49, 64, 81, 100, and so on. Those are the values that you should try dividing the number that is underneath your square root by to see if you can simplify that square root any further. So 48, if you've got your calculator slash when you have your calculator right next to you, take that 48 and divide it by any of these perfect squares. You want to try to find the largest perfect square that fits into 48. Hopefully you're able to see that 16 fits in to 48. We can break this down into 16 times 3. 16 is a perfect square, so that means we can take that number out of the radical. The square root of 16 is 4, so we would write our final answer as 4 on the square root of 3. Now, we know that we have simplified it completely if that number that is stuck underneath the radical cannot be broken down into, cannot be divided by any more perfect squares. So 3 is prime. It is the furthest we can break that answer down. So box that answer, and we are good to go there. Our next problem, this bottom left corner, let's give this one a shot. First of all, label your side across from the right angle as your hypotenuse. Label either leg A and B, and let's go ahead and plug into the Pythagorean theorem. Leg squared plus leg squared equals the hypotenuse squared. So we have ourselves, if you want that x squared to be on the left, just because you're used to it, you can move it around. X squared equals 244. Take your square root, just like we did before, and we get x equals the square root of 244. Just like before, make sure that you're taking that 244 and figuring out if any of those perfect squares from above fit into it. Pause the screen if you need to, and make sure that you're trying dividing by those numbers before we go on. The largest perfect square that fits into 244 you probably found was 4. 4 fits into 244 61 times. 4 is the perfect square. Take the square root of 4. The square root of 4 is 2. So we have 2 on the square root of 61. We know that is the furthest that breaks down because 61 is a prime number. It also is not divisible by any of those values up above. So that is our final answer. I expect your answers to be in simplified radical form on your assignments as well. Let's go over and take this Pythagorean theorem to a word problem type setting. If you're taking these notes by hand, you do not need to write this entire word problem down. I just want to make sure that you get the part that I'm writing down on your sheet. So let's see here. They tell us in baseball the distance between each base is 90 feet. Determine how far the catcher has to throw to get the ball from home plate to second base. Let's make a little visual for ourselves of a baseball diamond. It's actually just a square. And you know that home plate is right here. We've got first, second, third, and back to home. They're telling us that the distance between each base is 90 feet. We want to find how far the catcher remember sits behind home plate, has to throw to get the ball from home base all the way to second base. Now, just like I said, even though it's called a baseball diamond, it is a square, so these are all right angles, even though I didn't draw it perfectly, it doesn't look like it. So if we turned our screen a little bit, we'd see that we have a right triangle. We have 2 right triangles, but you only need to really look at one. 90, 90, and we're trying to find this long distance. Label your sides, so we have A, B, and C, and try plugging in to the Pythagorean theorem. Pause the screen if you want to try it on your own. Now, since this is a contextual problem and they're actually asking us how far he has to throw, we're not going to leave it as a simplified square root. We're just going to go ahead and plug that square root of 16,200 into your calculator. When you take the square root of that value, you get 127.3, and make sure you label your answer. We notice from above that it is in feet. So the catcher has to throw 127 feet to get from home plate to second base. Pretty far away. Shout out to all you catchers out there. Now, when you're dealing with the Pythagorean theorem, there are some really nifty values of the legs and the hypotenuse that show up over and over again. We call those common Pythagorean triples. So if you have legs that are 3 and 4, the hypotenuse is always going to be 5. This 3, 4, 5 style triangle always shows up on the ACT. So that goes for multiples of 3, 4, and 5 as well. So let's say we multiply the 3 times 2. 6, 4 times 2, 8, 5 times 2, 10 is also a Pythagorean triple. So if we knew the legs were 6 and 8, the hypotenuse is always going to be 10. It allows you to save time when you're doing a Pythagorean theorem problem if you can recognize that Pythagorean triple. Another one that often shows up, 5, 12, 13, and multiples of it. Another common one that you'll see often on the ACT, 8, 15, 17. So if you can get those through your noggin, memorize those, you won't even have to do all the work that we did above. You can just plug in the missing value. There are tons of those, by the way. If you're really interested in them, you can Google them and they will show up. You can, there's infinite number of them. It's pretty cool. But those are the most common. So that's Pythagorean theorem. If you need to rewatch anything, go ahead and rewind the video now. All right, the last thing that we're going to be tackling in today's notes are special right triangles. Special right triangles are special because they are right triangles whose sides work the same way proportionally every single time. All right, so the two types of special right triangles that we're going to deal with are that you'll see are 30, 60, 90 right triangles and 45, 45, 90. When you are dealing with a 30, 60, 90 triangle, the sides work in this proportion. The side across from the 30-degree angle on the other side of the 30-degree angle, we label X. The side across from a 60-degree angle, we label X square root 3. And the side that is across from the 90-degree angle, or the hypotenuse, we label as 2X. The sides, no matter what number X is, will always move in that proportion with one another. Now, I want to go back up to this special right triangle title, and underneath it, I want you to write this lovely word, memorize. You will see special right triangles all semester long. The quicker that you can figure out or remember these proportions, these labels, the better. So that is a 30, 60, 90 triangle. A 45, 45, 90 triangle is an isosceles right triangle. Because these two base angles are equal to each other, the sides across from them are also equal. We label those with X. The hypotenuse is whatever the leg is times the square root of 2. Again, memorize. You've got to know those sides of a special right triangle for the rest of the semester, really rest of the year. Let's flip it on over to the back. So first things first, when you're finding missing sides of special right triangles, you're going to want to first figure out what kind of special right triangle you're dealing with and then label your sides according to what angle is across from it. So we look at this 30-degree angle. I'm going to ignore the 7 right now. I don't even care about that right now. I'm just labeling the side across from the 30-degree angle X. Label the side across from the 60-degree angle, X root 3. And the side that is across from the 90, the hypotenuse, 2X. Label first every single time. Then you're always going to be given at least one side. So I'm going to look at this triangle and I'm going to notice, oh, I'm given the side that is labeled x. This is the easiest style. We know that that x value, oops, not highlighter, x is equal to 7. You take whatever that label is and set it equal to the value that is given to that side. So we know that x equals 7. Now we take that value of x, sorry, and plug it in wherever we see an x. So we know that this long leg is x root 3, meaning if x is 7, this long side is 7 root 3. The hypotenuse is 2 times x. Well, if x is 7, 2 times 7 gives us a side length of 14. We have now found all the missing sides of that special right triangle. Notice how we couldn't use the Pythagorean theorem even if we wanted to because we only had one side. In the Pythagorean theorem, you need at least two. Move on over to the right triangle, to the right. And let's label our sides here. Again, I'm just ignoring that 3 root 2 for right now. I'm just labeling my sides. So we have the two legs in a 45, 45 are 45, 45, 90 are x. The side across from the 90-degree angle is x square root 2. After you have labeled, find the side that you have been given and connect those together by putting an equal sign in between them. So we know x root 2 is equal to 3 root 2. Now, at this point, you might very well recognize what x is going to be. If not, if you still need to solve, no big deal. We want to isolate x. To get rid of that root 2 that's right next to it, we would divide by root 2. The root 2's on the left cancel, as well as the root 2's on the right, and we get ourselves x equals 3. We take that x equals 3 and plug it back in to our other side lengths. So we know that both the legs here are 3. Continuing on, this middle left problem, we know that that one angle is 60, another angle is 90, so this remaining angle has to be 30. There's only 180 degrees in every triangle. Again, ignore the 8 for right now. All we're worried about is labeling our sides. The smallest leg across from 30 is x. The larger leg across from the 60-degree angle is x root 3. And the hypotenuse, you label 2x. Please, please, please get used to labeling those so that you can get those proportions, those side labels in your head. You will need them, need them, need them. Okay, then back up and think to yourself, okay, I'm given one side length. I'm given this side length of 8. Set those two sides equal to each other. Sorry, set those the label equal to the side length. So we have 2x equals 8. Solve for x. You should get x is 4. Now, since we know x is 4, wherever we see x, we're going to put 4. So on this missing short leg, we know that side length is 4. And for the longer leg, we would write 4 root 3. Moving right along. This one might look a little different to y'all because you're like, I only see a 90-degree angle. If they tell us that these two sides are equal, that means that those base angles are equal. It's a 45, 45, 90 triangle. Label your sides. The two legs are x. The hypotenuse is x square root of 2 in a 45, 45, 90 triangle. Look for your label. The side length that you're given and the label that's right next to it. Set those two pieces equal to each other. Divide by the square root of 2. Now, in this problem, the square root of 2 did not cancel out on the right side. We would not keep it as 6 over the square root of 2. We need to rationalize that fraction, meaning we cannot leave a radical in the denominator of a fraction. To rationalize, you multiply the entire fraction by that radical that is in the denominator. So I'm going to multiply by square root of 2 on the top and bottom. 6 times the square root of 2 is 6 root 2. And square root of 2 times square root of 2 is square root of 4. But hopefully you know that square root of 4 is Just 2. When you multiply a radical times its twin, the radical goes away. Last thing we can do here, look at the coefficients out in front. 6 divided by 2 is, of course, equal to 3. So we know that x is equal to 3 on the square root of 2. Now we'll take that 3 root 2 and plug it in wherever we see x. So we know that both of these legs are equal to 3 square root 2. Pause if you need to and look back over that. I would like you to pause and try this problem on your own. I, of course, will give you the answer and go over it, but give yourself a chance to try this problem on your own. Pause the video. Hopefully you've tried that problem on your own now. Check your answers. You should find that this short leg is equal to 5. The hypotenuse is equal to 10. I want you to try one more on your own, and that's this problem to the right. Pause the screen, try that on your own. Okay, check and see if you're able to first label your sides correctly, like my ink in blue, and then check to make sure that you set up this equation, x root 3 is equal to 18 over here. When you divide by root 3, again, just like the problem right above it, we have a radical that is in the denominator. Rationalize by multiplying by square root of 3 over square root of 3. That gets rid of the radical in the denominator. You have 18 root 3 over 3. 18 divided by 3 is 6, so you should get that x is equal to 6 square root of 3. So we'll now take it back to the problem, and wherever we see x, we will plug in a 6 square root 3. So that means our short leg is 6 root 3, and our hypotenuse is double that, so it's 2 times 6 root 3. When you're simplifying that, these coefficients out in front would multiply, so you get 12 root 3 is your hypotenuse length. Your homework will go over those special right triangles again, as well as the Pythagorean theorem. Come prepared, ready to ask questions in the last 10 minutes of class if any of this was confusing to you, or if you need me to go over any other problems. Great job, y'all.